the quite strange fact is that even in the first text that tells us the story, the total number is written and is known exactly, and it's a big number. So we don't know exactly how this was computed, but the first writing that explain an interesting method, an explicit mathematic method, comes from Fibonacci. Have you ever heard of Fibonacci? Probably. He wrote in the beginning of the 13th century a book named Liber Abaci. It was written in Latin, and Liber Abaci means book of calculation. It was at a time in which there was an important fight that started in the 10th century and ended only in the Renaissance about the best way to make calculations. The old ways in Europe was the use of abacus. You know what abacus is? It's a kind of a table, and you put columns on it, and you put grains or things like that, and you can add, subtract, multiply. It's a very practical tool. And the other proposed way of making calculation is the way we use nowadays, well, still before computers, of course, is writing numbers and, addition algorithm and subtraction algorithms. And this came from India and was used by mathematicians of the Arabic culture. And it came to Europe by the Arabic culture mainly, but also people went to North Africa or even Egypt, from Europe to Egypt or to North Africa, and discovered, wow, there's this new way of writing things, from Indian origin. That's very good, but still it's not good for us. We're different. We don't want that, and it took several centuries for that. And Fibonacci is one of the first European, it's not really mathematician, he was more merchant, to say, well, let's use this way of writing numbers and make calculations. Let's forget the abacus and let's write things like Arabs and Indians. And so the Liber Abaci is really a kind of promotional book for Indian numeration system. And so in the Liber Abaci we find the question of the number of grains on the chessboard without any reference to the legend of the King of India. He just considers the mathematical problem, and he solves it. He solves it. This is a way for him to show that, well, really we can use big numbers with this Indian and Arabic way of writing numbers. It's very practical. Let me show you. I can compute very good, very enormous, huge numbers without any problem. So his way of doing this, so how to compute 2 to the 64, is what is known today as algorithm of fast exponentiation. So you start with 2 times 2. It's not very difficult, of course. You get 4. That is 2 to the 2. Okay. Then you multiply 4 by 4 to get 16, and this is 2 to the 4. Okay. Then you multiply 16 by 16 to get 256, which is 2 to the 8. Okay. This is much faster than to multiply 2 by 2 by 2 by 2 63 times. That would be very long, and very long means probably many mistakes in the calculation. Here we are already to 2 to the 8 without any difficult calculations. Then things become a little bit more complicated, but it's not that complicated. We get 65. Difficult in English. 65,000 and well, you write it. So 2 to the 16. Then 2 to the 16 times 2 to the 16 gives you 2 to the 32. It's not that big. I don't know if in India you still train yourself to this kind of calculations. In Europe, you don't. We don't. We don't. Well, it was now there are computers, and we don't do that again. And scholars don't do that anymore. I think it's not that clever, but. I hope that in India you should be able to do that without any mistakes. But when I give this to my students in general, they fail, and especially when I give them the last step, they all fail. It's very difficult for them. So Fibonacci gives the final number, which is here. Oh, big number in English. Ooh. 18 trillions 446 billiards 744 billions 73 milliards 709 millions 551 616. So you heard a number in French. There are a lot of people when you talk to them with this kind of number. A question is, how do we name it? And it's quite important. And when we become mathematician, we realize that the name of its exact name has no real importance. But for a lot of people, it's important to just say it. Well, how is it? So, also there is a difference between French on some part of English-speaking countries to short scale and long scale to say numbers. So. I think in India it's the English way of saying numbers, so million, billion, trillion, etc. In France we have million, milliard, billion, billiard. So it allows us to say many more big numbers. It's easier in French, but well, it's less regular because yon, yard, well, whatever. Oh, so this is, of course, this is not the exact number, because we have to subtract 1, of course. So the right number is 5 instead of a 6 because of the last grain. We know that the total numbers is not 2 to the 64, but 2 to the 64 minus 1. Okay? So, indeed, this is a huge number. We understand that it is a huge number. And we could give the exercise to find out how many years would be necessary for an Earth fully each year how many grains of wheat are we able to produce, and knowing that how many years would it take to get that many grains. And even nowadays, that would take centuries. It's really a huge number. But so the way Fibonacci gave us is interesting because it's quite short. This is not a very long calculation. The last one is quite long, of course, but this is, well, we understand the thing. But still, there is a problem to get the result and to accept the result. That means, okay, this is a big number, but even the calculation is not enough in general to accept the idea that from so small numbers, 1 grain on the first one, you multiply by 2 and you have 64 places. That's not big numbers. How these small numbers are able to produce such a huge number in the end. And this, even after the calculation, there is something like a failure for our intuition. That means that we're not able to accept directly, in general, of course. It's difficult to accept that such a huge number is produced, even when the calculation is done. This has been studied by psychologists. It started in the 70s. It's called the exponential bias. Okay, bias. Okay, that means the exponential bias is well, you put the curve y is 2 to the x, so with the exponential notation, you can see it as the number of grain. Here are the places. Here are the number of grain on each place. The specificity of such an exponential curve is that in the beginning it's not well, it's quite flat. So 1 grain, 2, 4, 8, 16, not that much. And then from the 30th place, it becomes huge, and then it goes extremely fast, and faster than our brain seems to be able to imagine, at least in the first place. So the idea was that in our brain we're not really able to imagine this curve, and we imagine other kind of curves that looks more like that. So that means that when we try to imagine how many grains on the chessboard are there, we add grain instead of multiply them. That's the way our brain works. Sorry. So, but the fact that the exponential growth of grains on the chessboard is so enormous had been understood in several ways in general society. And first, we have some consideration about dreams of abundance, of wealth. And there are two kinds of dreams on this way. Because, oh yes, I'm really sorry. The first one is, and that's interesting to mention that in the tale of the grains on the chessboard, and the King of India, they are in fact in the different versions we have. Some of them consider grains of wheat. But some others, and this is the case for the oldest version we have, multiplied by 2, not grains, but dirhams, which is an old monetary unit. 1 dirham as well, 1 rupee, say, okay, 1 rupee. And that's very interesting, because you produce as many dirham as you can produce grains in the story, but at the time, this was not that different. Because of economical consideration, what was coins? Billets. At the time, when you had a coin, its value was in itself because it was in gold or in silver, and its weight was defining its value, because gold has this value. So you take a coin of 1 gram and this has this value, and you write this value on the coin. That's it. Nowadays it's very different. Nowadays we have sheets of papers on which we write numbers, and the state tells us this is 1,000 rupees. No, 1,000 rupees. Yeah. I know that in India there was you are especially aware of the difference between old and modern way of considering monetary units. It's fiduciary, maybe fiduciary. I don't know. It's I'm not sure of the English word. Fiduciaire, monnaie fiduciaire. It's because you are confident that the state the state says this have this value, so you're confident, and you say, okay, this is this value. Modern economics relies on this, but old economics did not. So at the time, in the 9th century, grains or dirham was essentially the same kind of things. It was riches was based on concrete things. Not on what the state says this has value and this has not. So, even if at the time money or grains of wheat could be considered the same, it was already the beginning of a difference, and it provided already two ways of conceiving riches. First one is when you consider riches, you multiply dirhams, you multiply money. The one who did that first was an Englishman named Richard Price, who wrote a book in the end of the 18th century, said observations on reversionary payments, in which he asserted that a penny, so a dirham if you want, a rupee if you want, a small amount of money, placed at the time of the birth of our Savior, so our Savior for him was Jesus Christ, at 5% of compound interest would have grown to to an amount bigger than the amount amount of money, more important than 200 million times all the gold on earth. Probably he didn't know about the legend of the King of India and the grain of wheat, but he had the same kind of idea. But it was for him a kind of political prospect. He said a state could do that. A state could place to compound interest some money, and then in some centuries, that is the scale of time in which a state can live, the state would become very rich, and that would be very helpful for everybody. He indeed believed that. So this is for the dirham part of the story. Say how to create infinitely many riches, simply because you multiply a penny or a dirham. And the other kind of riches, of wealth, is when we multiply grains. And when you multiply grains, we find one more time Fibonacci with his famous problem of rabbits. This is probably the reason for which you know Fibonacci, for the sequence of the the Fibonacci sequence. So it's not a very good translation, so you shouldn't write it. Maybe you'll find a better one on the internet, because this is a good French translation, but I translated in English, so it's not very good. I did it too late to be a good one. But the idea is that, well, there is some kind of way of generating rabbits during the time, and this problem is. Does everybody know the problem, the Fibonacci problem, or should I mention it in deeper? Okay.
Everyone is aware of Fibonacci problem?
No. Okay. So that's not a problem. Okay. So let me say it. So the problem is you have one pair of rabbits, and they will reproduce. They will generate other rabbits. And the rule is the following: each month, a pair of rabbits generate another one.